We have today we have a first, being the first CRG, which means the collaborative research groups, the beamlines at the ESRF that are operated by individual countries. And today we have the UK BM28 beamline and Didier Wermeille, who is going to tell us a little bit about the beamline. The beamline started out as a very specific tool to study magnetic properties with X-rays. And I think that's also something to keep in mind, that the CRG beamlines are really a strong point of the ESRF portfolio, because they bring really specific capabilities to the ESRF. And now we leave the floor to Didier to tell us everything we ever wanted to know about XMaS, and we're just afraid to ask. So please take it away.
Thank you, Tillman, for this nice introduction. Thank you, the user office, for organizing this, and especially thank you to the user organization, the ESRF user organization, to allow both ESRF and CRG beamlines to present their breadth of opportunities. So today it's BM28, it's the UK material science beamline at the ESRF. And I'm gonna tell you a bit about what we do here at XMaS. A little background, XMaS in a nutshell: we are part of a portfolio of facilities of the UK RI, Research and Infrastructure. We're sponsored by ESRF, and we are one of the national research facilities. Those facilities are world-class facilities for engineering and physical sciences. So we're part of about 18 or 19 of those, bringing the best of the science for us in the X-ray science. XMaS has been an integral part of the UK synchrotron radiation infrastructure since 1997, and we are working in partnership, obviously, with ESRF and with the Diamond Light Source. It's a joint project funded by ESRF and run by the universities of Liverpool and Warwick. And XMaS provides free at the point of access to synchrotron radiation to UK and international users. It started as the X-ray magnetic scattering XMaS, and over the years it has changed to reflect the needs of the community. It's still XMaS, but now it's the X-ray material science beamline. And if you want to know more, go on our website, www.xmas.ac.uk. A brief history of XMaS. Discussion started in 1990, and the first proposal to finance the project was 92 with 60 kilo pounds at the time. 1994, beginning with the first grant for the design and construction of the beamline. And then XMaS magnetic scattering beamline was going to be on port D28 of the ESRF. 1997 marked the inauguration of XMaS with the first beam, first users, so the birth and baptism of the beamline. We're running on about 4 or 5 year grants. The second grant was in 1998, where actually XMaS became UK mid-range facility. And then in 2012, we got the third grant for becoming a UK ESRC national research facility. In 2018, we managed to succeed the funding of the fourth grant, despite the EBS, or thanks to the EBS coming at the ESRF. It was difficult because we would go dark for about 2 years, not knowing at the time, or it was a little less, but not knowing at the time COVID would hit towards the end of that period. But ESRC was confident we would benefit from this ESRF EBS upgrade. And so in 2024, we managed to succeed the fifth grant for XMaS. So we funded until January 2029. The layout of the beamline is very simple. We're now on the new short band dipole of the EBS lattice of the ESRF with a dipole of 0.86 Tesla. That allowed us to increase the high energy by a factor of 2. XMaS at the beginning was sitting on the 0.4 Tesla part of the long bending magnets of the initial ring. So we more than double the field, so we more than double the critical energy. So now we can have, I mean, you can see on the top here our flux up to 40 kV. We actually can go even further than that, as you will see. And so we are working, our first optical element is a cryogenically cooled silicon 111 double crystal monochromator with a very large angular range, which means it lets us cover the tender energy part of the X-ray spectrum below 5 kV. We can go down all the way to 2.035 kV. And we can reach at very low angle of the mono 47 kilo electron volt. We have as a second element focusing mirrors, 2 of them, silicon substrates. One is coated with platinum, which allows us to go to 47 keV, and the other one with chromium that starts to cut actually below 20, but we can use it to 21 kV. They're mounted at 2.5 milliradians, and it's roughly a 1-to-1 focus configuration. They're in the middle of the beamline, 25 meters from the source and 25 meters from the sample. And at the sample, we have a 6-circle diffractometer, the geometry 4S plus 2D, where we can have a lot of different sample environments. We have harmonic rejection mirrors when we want to work at lower energies, very important to cut those higher harmonics. And then we can also play with the incident polarization of the beam. And our beam looks like slightly more elongated in the vertical, but we have about 80 by 80 micron beam size. What is XMaS? Actually, XMaS, it's the Swiss Army knife of synchrotron radiation techniques. We are covering a wide breadth of techniques, going from scattering with small angle in geometry, grazing incident geometry. We can do wide angle X-ray scattering, reflectivity, resonant magnetic reflectivity. We do single crystal diffractions. We do some powder X-ray diffractions, and then we do resonant elastic X-ray scattering or resonant magnetic X-ray scattering, reciprocal space mappings, and we also have surface X-ray diffraction possible on the beamline. And for spectroscopy, this is rather, okay, it's not so new anymore, but this is the latest addition to basically the XMaS portfolio with XANES, EXAFS, and X-ray fluorescence. So if there's only one slide to take away, this is this one from this talk. On the left here, you have the summary of all the techniques. They can be done individually or in combination. In a very wide sample environment that is mountable on our diffractometer, going from solar chamber or Lincoln cell to flow gas cell. As I said, we have phase retarders to play with the incident polarization, so we can switch from linearly polarized to circularly polarized in the range of 2.4 to 13 kV using diamond crystals or silicon thin wafer, and then we can also do a polarization analysis of the diffracted beam. We have a series of magnets for different geometries. We can apply voltage across the sample, so with electric field up to 10 kilovolts per millimeter. And then we have a set of cryostats where we can actually go from 1.8 to room temperature with cryofurnace to go to 10 Kev to 700, Kelvin, 1.8 Kelvin to 700 Kelvin. And then, I mean, for the cryostat to room temperature, and then from room temperature, oh, from 10 Kelvin to 700 Kelvin. We also have furnace on request, and we have a vacuum chamber or helium chamber for spectroscopy measurement, especially in the tender X-ray regime. And all this in a very broad range of applications. The diffractometer, this is SICK geometry. It's been fully refurbished during the ESRF EBS shutdown. It's a non-magnetic, and it's got two theta arms, so we can have here vortex silicon drift diode for like point detection for high resolution, and we have another arm for 2D detectors. So the energy range from the tender regime to 47, it's difficult to do diffraction at so low energy because of the reciprocal space. But we have some chambers where we've done some experiments. And then sometimes this diffractometer is like a fairly expensive sample holder for some experiments where the 2 theta arm is actually not needed. We have a wide suite of detectors going from point detectors. Since we've been doing a lot of spectroscopy in the past 10 years, we've increased the range of detectors. And since after EBS, we moved to way past 20 kilo electron volts. We just recently bought a germanium 7 element detector. But we have a 2 millimeter thick silicon drift diode and a 4 element vortex drift diode also. For 2D detectors, 2 Pilatus 300K that goes on the diffractometer, a 1M that sits on a rail mostly for Sachs wax. It's too heavy to go on the diffractometer, unfortunately. We have a small 2x2 MaxiPix detectors, and for high energy, we have also a CATTEL lambda detector. And sample environment, a few cryostats here with beryllium window. So we've been doing rare earth material at the beginning and uranium or trans-uranium samples. So the beamline is equipped for this type of measurements. This is a low temperature 1.8 cryostat that goes into the 4 Tesla magnet, lithium cell. This is here our ball chamber for tender X-ray spectroscopy measurements, both in transmission or in fluorescence. We do some electrochemical measurements. So this is like a drop cell for electrochemistry. Interfaced actually with a potentiostat, galvanostat, so we can do the voltammetry. And then this is like a GISAX chamber for energy materials. So these are the 3 major magnets we have on the beamline. The 0.1 Tesla for in vacuum reflectivity, magnetic reflectivity measurements. We have here an electromagnet. I think it's plus or minus 1.5 Tesla that is possible to use. And this is our 4 Tesla superconducting magnet with, in this case, like the cryostat mounted in a vertical scattering geometry. So we can mount this 4 Tesla magnet in 3 different configurations with a field in the horizontal plane perpendicular to the beam or parallel to the beam, or the magnetic field vertical also, and then we could use the diffraction in the horizontal plane of the diffractometer. One thing that has been developed also is simultaneous measurements. for the standard setup here with an APD detector, but possible to apply voltage across the sample with a function generator, so we can generate different signals, and then an electrometer, and all this goes through the MUST card, and we can record the different signals at the same time. We've also used the ESRF ZAP scan, so the fast scan for spectroscopy, for a few months now, and so using also the MUST card and the signal from the monochromator, so we can go much faster with our spectroscopy with XMaS, especially XMaS measurements, instead of the traditional step-by-step measurements that we were doing until recently. This is an evolving landscape of science that we're covering. We used to do a lot more condensed matter, but the soft matter has increased, also materials for energy. And we are also in the healthcare science with teeth, human teeth, or the Komodo also teeth recently. A few highlights. I mean, since we're doing a very broad range of science, I've just selected a few examples on the left here. It's a simultaneous GISAX and current voltage measurements during in situ annealing of some perovskite photovoltaic. So using, in this case, using a Keithley voltmeter, but I mean, this again, this is like a combined geometry and combined techniques used for this example. This is an example in the tender X-ray regime here at 3.1 kV. This is the Palladium L3 edge for an operando experiment on measuring the XMaS on the sample. And then here on the left, I mean, what used to be the core experiments, type experiments of XMaS. So the 4 Tesla magnet, very low temperature. You can see like we went down to 1.8 Kelvin, studying the quantum critical point in this praseodymium platinum aluminum sample. And there's a very rich spin density waves forming depending on the magnetic field, the orientation of the sample inside that magnetic field, and the temperature. And so that was possible over a few beam times with these 2 publications, and some graphene surface structure in aqueous media here, some reflectivity measurements on the beamline. The thing I want to show here is like, because we went up to this high energy with our new dipole, short bent, and we purchased this Mirion 7-element germanium detector. It was commissioned recently. We had a few issues, but it was commissioned recently on the beamline, and we had like during the weekend of the 11th of November, a very happy user here, Professor Adrian Finch, with co-worker Anouk Borst, who actually measured the barium K edge in corals. And for them, XMaS is coming like almost a month, I mean, more than a month early. We need money to operate a beamline. So as I said, there was 94, 97, the building part of it. But then XMaS has been successful in securing grants from the EPSRC over actually six periods. And now we're funded until 2029. We get sometimes, oh, that's a recent possibility for us. We get extra money through calls, unmet capital calls for capital investment. The total has been 34 million pounds over, if I count from 94, sorry, to 2029, about 34 years, which means that we are about at 1 million pounds a year, or that comes to less than 2 cents per UK citizen per annum. This is, I think, a bargain for a UK and European and international science community. Tillman in his email was asking me what does make XMaS unique? And I was thinking there are a few things that makes XMaS unique. One is its stuffing. And actually he can say more about that, but we never say no. It's not possible. So if you have an idea, if you want to try something, if you want to do something, just come and knock on our door, talk to us, and we'll see what we can do. I just got an email today from somebody in Edinburgh who wants to do diamond anvil cell on the beamline. So I didn't say no yet. Another thing is our energy range. As I said, we go from the phosphorus K edge at 2.14, so we have 100 eV below that, all the way to the samarium K edge at 46.8 keV. So we cover the tender and the harder X-ray regime, and we can change the energy pretty rapidly, and basically try and hit the sample in the same position in any kinds of sample environment that is on the diffractometer. Versatility. So this is a good thing and a bad thing somehow. We change techniques almost every week, and we change configuration together. So in terms of efficiency, it's not ideal, but we are extremely flexible. As I showed you, you've seen plenty, the suites of equipment, sample environment, detectors. That's one of the after 30 years, we've accumulated a lot of expertise, and also in preparing those experiments and giving you users the best we can. And then I didn't show any slides, but we have also 2 offline facilities, one with a copper K-alpha microsource. So you can actually characterize your sample beforehand, or use it for experiments that don't require the synchrotron. We have a few records of publications coming just uniquely from that X-ray lab source. And then we have a sample characterization lab. And last but not least, XMaS is this little UK village in the Central Europe. This is done with people that have come and gone over the years on the beamline. The current staff is here. Our directors from Liverpool and Warwick, and co-directors. We have some admin support. And these are a few faces from a recent and not so recent past. That's it. And so I thank you all for your attention, and I thank all the users who potential and past ones that have come and want to come. And as I said, a bunch of information is on our website, xmas.ac.uk. Thank you very much.
Thank you, Didier. That was a great talk. I would invite the audience to put their questions into the Q&A box, so we can read them off and treat them a bit more efficiently. As Didier said, I mean, my first contact with BM28 was actually knocking at their door, asking them for a completely weird white X-ray beam and bringing my own detector, and they just said, like, sure, you come by and we try it out. And at the very least, it gave Didier some lobster tails for his barbecue. So yeah, for for you that we have 2 open positions next webinar. The next webinar is going to be ID21, X-ray microscopy. It's on the 12th of December. It's a brand new beamline. I was there just a couple of weeks ago. It's very exciting what they are doing. So stay tuned for that webinar in 3 weeks. And thank you all for joining us today. Thank you.